Attention, ladies and gentlemen. Welcome to another Lean Six Sigma for All session. This is a public session, so everyone is welcomed to this session. Please type from where are you taking this session right now. And what time is it for you? From where are you taking the session and what time is it for you? Okay, 2 p.m., 8 p.m., 8 a.m., 2 p.m., 2 p.m., 8 a.m., 7 p.m., okay, 3 p.m., 7 a.m. We have Colombia, Oman, South Africa, Saudi Arabia, Vietnam, Philippines, Poland, Mozambique, Trinidad and Tobago. My question for you is, are we part of a global team or not? Am I talking to a true global team? Yes or not? Guys, just a quick reminder that this is not part of your black belt program, okay? So all my black belt students, they have access to a training platform named Hotmart, and everything is there. Everything is there. White, yellow, green, black, and AI belt. If you are a master black belt student, you have master, black, green, yellow, white, and AI. So why am I saying this? This session is not mandatory for my black belt students, nor MBB. But if you want to refresh, if you want to have another another point of view of a topic that is there presented for you, you are more than welcomed. Marcelo, why are you running these public sessions on YouTube on topics related to Lean Six Sigma? So anyone can have at least a sample, at least a flavor, at least an idea of the topics that are part of our black belt certification program. Today, I'll be deep diving on hypothesis test. Okay, so what is hypothesis test? It's a fragment, it's a part of our black belt certification program. So type clear if this is clear. And the reason I'm saying this is because especially the new black belt students, there's a lot of FOMO, a lot of FOMO. Marcelo, I missed your session on YouTube. What do I do now? No. The content is there in Hotmart. If you want to stay here, you are more than welcomed. More than welcomed. Okay? Because there is always maybe a new angle, a different way to explain that may be helpful for you. But no FOMO. Type here for me. No FOMO. Fear of missing out. Yes? With love. I hope you guys feel the love. From my experience, in general, less than 1% of the belts Master black belts, green belts, yellow belts, white belts. But I'm gonna focus on black belts, less than 1% of black belts. Truly understand what is hypothesis test in terms of the basic concepts. Okay, so now I want to explore to guarantee and not less than 1% of my black belts. I hope all my black belts in the planet, they know what is hypothesis test. I'm saying less than 1% of the black belts in the planet, they truly understand what is hypothesis test. And today I'm going to deep dive in hypothesis test in the context of root cause analysis. Okay? We cannot measure population data in the vast majority of the scenarios in this planet. Type agree or type disagree. If I want to measure the height of the entire population of my city, everyone here in my city or in my country, in Brazil, this is practically impossible. It's impossible. It's impossible. You are producing 100,000 parts per day in your production line. It's practically impossible to measure 100% of the parts. And sometimes you do have capacity to measure, but sometimes you cannot find all the parts. Yeah, you may miss few parts. Are you guys following me? So if someone says, Marcelo, now I need to measure, I just accept, data that comes from the population. Very likely we would not have measurements anymore in terms of performance, evaluation. From 0 to 10, how much did you follow me so far? That like sampling is very helpful. Sampling is very helpful. So I got many 10s, but I got a 7 and an 8. So I'm gonna explain again, because if you did not fully understand what I said, we are in trouble. So I need only 10s. And be honest. Thank you for giving me a 7 and an 8. I'm gonna explain again. Let me give you another angle. Let's suppose we are producing Sherlene, Esther, and Esther, the two of you guys. I am producing acrylic parts. So I need you two to imagine, to picture a manufacturing line, of these acrylic parts, And let's suppose I need to measure one certain dimension, this dimension. And let's suppose this is a manual process. There is a person with this scale, and then I need to place it here and say 9.5 and write down 9.5. Let's suppose very manual process. From 0 to 10, how much did you guys understand me so far? Especially Esther and Sherlene. From 0 to 10, how much did you guys understand me so far? Yeah? So do you guys agree that I am consuming a certain amount of time? I'm consuming time and resource. There is a person, there is an equipment, there is time, And then let's suppose the manufacturing capacity is like of 1 million parts per hour. I am exaggerating, yes? 1 million acrylic parts per hour. And the measurement system is not as capable as the production. So I see there 1 million parts per hour. So if I go ahead and I need to measure 24 million parts per day. 24 million parts per day. I would need to hire, I don't know, maybe 100,000 employees. And I'm gonna need to buy 100,000 or 10,000 instruments like these. Are you understanding why? And again, I am placing a scenario on the extreme, yes? Like production line is, the capacity is very high and the measurement system capability is very low. Do you guys understand that this is just an extreme scenario? But things like that, challenges like that will happen all the time. All the time. There are many reasons. There are many reasons for us not collecting the population data. Time, resource, cost, you know. So if you guys understood, type sampling. Sampling is powerful. Type here, sampling is powerful. Yes, exactly. The theory of blood tests. Beautiful, beautiful connection. Beautiful connection. And random sampling, yes, will help us. Yes, sampling is powerful. We'll need. And what is sampling? Sampling is basically I have 1 million parts being produced per hour. And instead of measuring 1 million parts, I'm going to measure a portion of that. I'm going to measure 100,000 or 10,000 or sometimes 1,000 or sometimes just 10 parts. So a sample is a fraction, is a part of the entire population. Type good if we are good so far. And then let's suppose I have a sample, okay, of the width of the plastic part, okay. Yeah, beautiful. Of the plastic part, and then I have a sample by the size of 10. Okay, let's suppose I have only 10 parts. Yeah, only 10 parts. And then I have one 9.6, another one is 9.3, another one is 9.52, another one is 9.42, 9.4, 9.3. Yeah. Sample. What do we do with this sample? What can be done, you know, with this sample? What can be done? What can be done with, you know, like 10 data points, mathematically speaking? How can we explore this data and extract, you know, conclusions from this data set? What do maybe the majority of the people they would do with 10 data points? They would just go ahead and and calculate mean. Do you guys agree? The vast majority of the people would take these 10 data points and calculate the mean. Yes, exactly. Exactly. And so in the context of root cause analysis, remember that I have the width in baseline. Okay, so let's call this baseline. Yeah, or something like old machine, and then we have width with the new machine. Okay. And then I have old machine, new machine. So what you guys are saying is that we can, or to just to make it even more clear, even more clear. I could simply this is mean, right? And then what can I do with this result here? This is the old machine, this is the new machine. Is there any, can you see a difference here? Old machine and new machine. Yeah, so old machine 9.44, new machine 8.97. Yeah. So comments. Check if they are from the same population, okay? After mean, we check upper and lower limits. So let's understand variation, okay? Descriptive statistics, mean, mode, and median, okay? Normality test, okay? AQL. But I want to talk about, because remember, we have tools, techniques, concepts, and principles. I want to talk about principles. Yeah, principles. So can I go ahead and argue that the width of the acrylic parts for old machines is different from new machines? Can I just go ahead and do that based on these two numbers? I have one number for old machine and I have another number for new machine. Can I just go ahead and say old machine is different from new machine based on that? I can, but this is very limited. This is very limited. Very limited. Very dangerous, to be honest. Because see, 10 data points. This is sample or population. Type here for me. Let's talk about the old machine. I took 10 samples. This is I took 10 data points. This is sample or population? I took 10 data points. This is sample or population? This is sample. So if I go there and I select another 10 samples, different 10 samples randomly, okay, will I get the same 9.44? What do you guys think? What do you guys think? If I go ahead and I take another 10 samples, the population is there. I went ahead and I took 10 samples. Yeah. So if I go ahead and I pick and I select another sample, the result will not be the same. And if I take another sample, the result will not be the same. It will be different. Interesting. So do you understand that there is a probabilistic aspect to the mean? Yes or not? Or from this is important. So from 0 to 10, but now from 0 to 10, I'm afraid that you guys are biased, that I have intimidated you guys. Honestly, with love. If you are not a 10, type 8, type 7, and I'm gonna explain again in a different way. From 0 to 10, how much do you understand that? The population is there. Let's suppose 1 million parts. I took 10. I calculate the mean. I have a value. I took another 10. I have another mean, another average. I took another 10. I have 10 parts. I have another average. So I have variation in the means. I have variation in the means. So I can have an interval for the mean. I can have an interval from x to y to the mean. Yeah? Yeah. We are not yet talking about if the distribution of mean is the same of the distribution of your data, of your population data. We are not talking about, yes, for sure, we can make mistakes on any sampling strategy. Yes. Yeah. But my point right now is only this. I have just one single point. Do you understand that when I pick different samples, I'll have different means? And so I have a distribution of means. I have a probabilistic aspect to the mean. Do you understand that? Yeah. And then we may use different techniques, but if we take this famous, the simple ANOVA one way, what do we have here? What do we have here? I have the mean for old machine. I have the mean for new machine. Yeah. And I hope you guys can see. I have an interval. I have an interval. Yeah. I have an interval. And this interval has to do with all data points or with the mean? This interval has to do with all data points or with the mean? What do you guys think? This interval I'm talking about. So take a look here. Let's sort for the old machine, okay? So it goes from 9.3 to 9.6, 9.3 to 9.6. So 9.3 is here. 9.3 is here. So it is not part of the interval. It is not part of the interval. So this interval is not the interval that contains all data points. No, no, no. It's an interval that suggests possible values for the population mean. I am saying based on this sample, I want to tell you that the population mean is anywhere from, take a look here, 9.359 and 9.51. Yeah. You know that here it's not exactly plus or minus 3 standard deviations. It is not. Because when you have plus or minus 3 standard deviations, you have 99.73. For 95 is the famous 1.96. 1.96. But it's not exactly the same mechanics of control charts. It is not. Because here we are not using the standard deviation. Yeah, we are using the standard error. That normally it's the standard deviation divided by square root of sample size. The mechanics is similar, but it's definitely not 3. Do you understand that? Definitely not 3. And then we may explore like this in many different ways. Let me show you guys something. Let's suppose I take from one certain population, okay, 10 data points, and let me create from C1 to C20, okay. The mean is 10, standard deviation is 1. Okay, so I know that this is population. I'm asking Minitab to generate 20 data sets by the size of 10. Mean is 10 and standard deviation is 1. This is parameters, okay? Parameters from the population. So, okay, I have 20 data sets. 20 data sets, okay? If I go ahead and I plot these 20 data sets using interval plot, yeah? I believe here it will be easier. Let's see if we can do that. I'm gonna add a reference line, okay, that is 10. And you guys tell me, what was the population mean that I put? What was the population mean that I put? You guys tell me. Yeah. This is good, but this is not the. I would love to have like one that is the perfect one. Let me generate another random data, even knowing that it will not happen always, you know, but I would love to have a perfect example for you guys. Yeah, this is the perfect example. No, this is not yet. Not yet, not yet. I think now, yes, now we have the perfect example. Okay, the perfect example. How many intervals do we have? How many intervals do we have? No, how many intervals? Intervals. No, it's not 40. It's 20. Perfect. It's 20. We have 20 intervals. Okay? All these intervals, they come from random samples. So we had like 20 samples from the same population. The same population. Okay? So what is the concept of confidence interval? At the 95% confidence level, I have an interval that represents 95% in terms of confidence level. So what does it mean? It means that if I plot 100 intervals from the same population, the true mean, and we know that the true mean is 10, the true mean will be included in how many intervals? I have plotted 100 intervals. They are different. If I calculated the extremes, the limits, the intervals, if I built the intervals at the 95% confidence level, it is expected, it may be 96, it may be 94, it may be, yeah, it is expected that the true mean is present in 95% of the intervals. Type beautiful if you understood that this is beautiful. So 95% confidence interval, it is not like there is 95% chance that the true mean is there. No. If I plot 100 intervals, yeah, in 95% of them, the true mean will be there. Less than 1% of the black belts in the planet, they know that. Very few people know that. Very few people know that. Very few people understand that. Because see, if I have 20 intervals, I'm gonna see 10, number 10, take a look here, 10 in how many intervals? I should see 10 in how many intervals? If I have 20 and I am operating at 95% confidence level, I should see the population mean in how many intervals? Beautiful Excel machine, Excel engineer, beautiful Aquila, beautiful quality pro training, beautiful Simon. in 19? Because 19 out of 20, it's 95%. You may cry. Now you are allowed to cry. Type here tears if you are in tears. And you guys saw that I was generating random data again because we got 18. 18. So sometimes you may have 18. Sometimes you may have 20. Sometimes you may have, for this sample size, very unlikely you would have 17. But 18, 19, 20, yeah? This is beautiful. This is beautiful. So, hypothesis test is part of an umbrella that we call inferential statistics. We are all the time inferring. We are projecting. We are looking at a sample and we are trying. Let's be humble. We are trying to understand the population. I'll say that again. Inferential statistics, hypothesis test, is part of an umbrella named inferential statistics, where we are trying to, based on a sample, to understand the population. But it's, I don't know if you guys agree, but this approach here is way more robust, way more sophisticated, way more complete than just calculating the mean. Do you guys agree? This is way more beautiful, way more robust, way more complete than understanding, than simply calculating mean, you know? So, and then if you are my black belt student, you know that there are many different types of hypothesis tests. One sample t, two sample t, one sample sign, one paired t-test, one sample z. There is a one proportion, two proportions, chi-square, ANOVA, Moods median test, Kruskal-Wallis. There are many different hypothesis tests, but the mechanics is the same. So if you understand what I'm saying here, it's the same. We are gonna collect a sample from one extreme in your root cause analysis, for example, old oven, and another sample in the new oven. Marcelo, what about sample size? What about the fact that the sample should be random? So the five rules for sampling are, if you guys want to take note, your sample should be sufficient. Here we are talking about sample size, and I'm gonna deep dive on that a little bit more in a few minutes, okay? It should be reliable meaning your data comes from a reliable measurement system, okay? Your data should be well segmented. Your sample should be well segmented, meaning if I want to understand my students from the Philippines, and I I have a certain number of students as my population, and I want to understand my students there, I need to collect data from the Philippines. I cannot, if I want to understand the Philippines, I cannot have students from South Africa, for example. Simple like that, but believe me, we make a lot of mistakes because sometimes we just go global. And then we get, or sometimes we get the samples that are easier to get. So you need to avoid, as much as possible, any sort of bias. So again, your sample should be sufficient, and here we are talking about sample size. I'm going to explore this a little bit more. Must be reliable. It must come from a measurement system that is reliable. It must be well segmented, so according to your research objectives or your root cause analysis, yes, or your project objectives, okay? From 0 to 10, how much sense is it making so far? Yeah. Beautiful. Then, after I select my sample strata and also my sample size, I need, for example, 10 samples, 10 students or 50 students from the Philippines. After I do that, I need to go ahead and select these students, okay? How do I do that? How do I do that? I need 50 students from the Philippines and I need to know if they are happy or unhappy with my sessions. Okay? How do I collect that? Can I go ahead on a Friday night at 11 p.m. and I see 50 students from myself just coming back from a party, and let's suppose they are a little bit, you know, yeah. Can I collect this? I need 50 people. My measurement system is reliable. It's well segmented. It's from the Philippines, but I am collecting on a Friday night all of them from the same cluster. Let's say there are 50 people on a Friday night that probably they are super excited, you know, they are maybe overly happy and a little bit of alcohol maybe. What's the problem? The problem is my sample is not random and I need to have a random sample, meaning let's take few people on a Friday, few people on a Monday, few people on a Tuesday, few people from Manila. Is that right? I'm sorry for my poor knowledge about the Philippines. Manila, I think it's the name of the city, the most important city, and a few students from another city in the Philippines. Are you guys following me? Yeah, I will still be partying. Yeah, so see what the Excel engineer said. They will not properly represent the population. So your sample must be contextual. Contextual. Meaning when are you selecting? And sometimes there are some variables that are not impacted by when. There are variables that you can pick at any time. But depending on what you are measuring, when matters. So again, your sample must be sufficient, your sample must be reliable, well segmented, random, and contextual. Okay? If you take proper care of these 5 dimensions, you maximize the chances of having a representative sample. Representative sample. Okay? And Marcelo, what about sample size? Ooh, sample size impacts a lot of things. But the easiest way to understand what is maybe one of the most critical impacts of sample size is the interval, the confidence interval has the square root of sample size in the denominator of the standard error. So when you increase the sample size, you are doing what with the standard error? If the standard error is at the denominator of, if sample size is at the denominator of a standard error, what do you do with standard error when sample size goes up? It goes down. So normally when your sample size goes up, your confidence interval shrinks down. Does it mean that you are getting more confidence? No, you are still operating at the 95% confidence interval, but your interval is now shorter. You are narrowing down your interval, meaning that you are gaining precision, precision, precision. So you are saying, yeah, you were saying, for example, on a practical point of view, you would see, the intervals here, all of them shorter. Oh, Marcelo, so it means that we would not have 95% of the intervals containing 10. Not necessarily. Yeah, not necessarily. Because you see the intervals getting closer as well. Yeah. And then there is another conversation about central limit theorem, that the distribution of means will tend to normality when you increase the sample rate, the sample size of the groups. Yeah. So if instead of collecting 10, I collect 30, I collect 100 per group, I am maximizing the chances of seeing in the distribution of means, normally distributed. This is the famous central limit theorem, okay? Central limit theorem. So, if you guys understood that, when we run hypothesis tests like ANOVA, you know that we have two intervals, type two intervals, if you guys understood that. Two intervals, if you guys understood that. Two intervals. Yeah? And then, with these two intervals, one of the things that you can do is to find the famous p-value. Okay? And p-value, there are many different ways for us to reach this p-value. You can find here on YouTube my session about ANOVA. Yes, so it's really the integral, the area under the curve, okay, of, in this case, of the F distribution. Yeah, so what does it mean, like zero? What is that? What's that? So one of the ways to interpret this zero here is the intersection. Do you guys see any intersection here? Yes or not? You guys, give me just one minute, okay? Hello, hello, hello. Yeah, so there is no intersection, there is no overlap. But then, what if I had a scenario like with machine C, okay? Then let's suppose I had here 9.5. Now let me run an ANOVA with the old machine and machine C. Is there an intersection? Yes or not? Yes or not? Yeah, can you guys see that there is an overlap here, there is an intersection here? Would you guys expect to see a p-value going up or still close to zero? Or zero? Would you expect to see p-value going up or still close to zero? What's the relation and differences with the samples for hypothesis test with definitions about sample size for an inspection plan? No, Henrique, yeah, we do not use hypothesis test normally, like specifically for inspection plan. For inspection, it's really a different conversation. Yeah, today we are focusing on root cause analysis, more focused on root cause analysis. And to be honest, believe it or not, you don't need initially to worry about your sample size. You can go with the sample size that you have. And then in case you have a p-value that is greater than 0.05, then you can do a power analysis, analysis of power. And then you can ask, for example, Minitab to tell you what would be the minimum sample size for us to prove a difference by this size with this standard deviation, for example. Yeah, power is the ability or capacity of reject the null hypothesis when we should reject the null hypothesis. And sample size plays an important role in this. We would expect the p-value to go up. Perfect. We would expect the p-value to go up. Yeah. So if we look here, we see that p-value went up. Yeah, differently from zero. Yeah, differently from zero. And then let me run another one here. Let me try to make the intersection even more clear. Okay, clearer. Then 9.5, 1. Let me see. Not 1. 0.1. 0.1. And then let me see if this is even more clear. Yeah, a little bit more, and then the p-value went up again. So again, there are different angles, different ways to see how does p-value behave according to the result of your hypothesis test. In fact, p-value is part of the results of your hypothesis test. But what I want to explore with you guys is I am collecting a sample or samples I am applying a certain mechanism, I'm using a certain strategy, and I am so looking at a certain number and I want to make a conclusion. In terms of root cause analysis, I am saying the root cause is validated, the root cause is not validated. Type clear if this is clear so far. In terms of root cause analysis, I am simply saying the root cause is validated, the root cause is not validated. Yeah? And then, what is the final part of this conversation about hypothesis test? We need to talk about the beautiful concept of null hypothesis, N-U-L-L, null hypothesis, and alternative hypothesis. Because see, if I am testing, I'm just checking, I'm testing a new machine for the production of my acrylic parts. The status quo, initially, the new machine will be the root cause or not. Initially, the new machine would change the performance of the process, yes or not? See that alpha is 1 minus confidence level. Confidence level is confidence level. Alpha is 1 minus. If confidence level is 95%, your alpha is 5%. So alpha is not confidence level, okay? Guys, I'll say that again. Every time that we run a hypothesis test, the status quo is there is no difference. There is no difference. There is no difference. I want to prove that my students, they get better salaries, better jobs after they become a black belt. If I want to prove that, I need to collect data to reject the status quo. The status quo is they come to the black belt and they have the same salary. They have the same jobs. That's the status quo. But then I find Alexandre, then I find Tarcísio, then I find Renan, then I find Henrique, then I find Sherlene, then I find Salomon, Kandasamy, that they have Kandasamy. I remember that he reported a salary raise, if I'm not wrong, or a promotion, a major promotion after he became a black belt, you know. So when I start collecting this data, see that I am breaking down, I am destructing the status quo from 0 to 10. How much do you understand that? I am destroying the status quo. Do you guys understand that? So I'm saying no. Without black belt, you are here. If you become a serious black belt, you are another professional. Root cause analysis, root cause validation. The status quo is we don't need to train people. Training does not make any difference. Okay, this is the status quo, this is the null hypothesis. But wait a second, if I compare trained people against not trained people, there is a difference in terms of performance. Whoa. So I am rejecting the null hypothesis. So almost always you will see as a null hypothesis mean A equal mean B. Proportion A equals proportion B. Distribution equals normality equals normal. Yeah. And then in order to, if I have this difference, p-value is high or low. If I have a difference, p-value is high or low. If I have this difference, p-value is high or low? It's low. It is low. It is low. And what is low? Low is less than 5%. P-value varies from 0 to 1. From 0 to 100%. Yeah? Or 0 to 1. So if p-value is less or equal than 0.05, or simply less than 0.05, that's okay, you should reject the null hypothesis, meaning, whoa, we found the root cause for your career being stuck. You need to do the black belt, Or we found the root cause for the high percentage of cheese bread, burnt cheese bread. It's because of the oven. Why? Because if I compare new oven with, old oven, we would see a p-value that is less than 0.05. And what's the conclusion when p-value is greater than 0.05? Then in fact it's inconclusive. It's inconclusive. It's like, does it mean that oven does not impact? No. What I'm saying is, at this point, I don't have evidences to say that the person is guilty. My father-in-law, he is the police chief of my city. He's a retired police chief. Yeah. So there is no innocent people. There is no innocent. There is guilty and not guilty. Not guilty means I don't have evidences to put you in the jail, to send you to jail. I am not saying that you are innocent. I'm saying that I don't have evidence. And it may be because of sample size. It may be because of sample size. If you increase the sample size, you may find something. And then obviously we need to be careful, because if your sample size is too large, you will catch anything. You will find all sorts of, we call this marriage. Yeah, when you live with a person for 20 years, 30 years, 40 years, you will find, your sample size is so large that you will see maybe everything, in terms of behavior. I'm not talking about cheating, guys. Don't get me wrong. Don't get me wrong. I'm talking about characteristics. Personality characteristics, physical characteristics. Because you are living with that person for so much time that your sample size is so large that then we start having a problem of statistical significance versus practical significance. You definitely don't want to have too much power, statistical power, because then you are too sensitive, because then everything is statistically significant, everything. And then when we find something being statistically significant, an effect that is statistically significant, we tend to say, okay, so now we need to control. Now I need to pay attention. And then if you are oversensitive, you are overreacting. Then you are paranoid. Then you are controlling everything. You definitely don't want to control, to say that, okay, what is important in this process? Everything. So you need to be careful with sample size in this sense, and obviously in terms of the size of the effect, because the simple fact that there is a difference that is statistically significant, it doesn't necessarily mean that it is important, because sometimes it must be statistically significant but with a certain difference, you know. I hope Brazil can perform better in the World Cup qualifiers if we get a new coach. And so if I collect some samples, random samples from previous games, and with different coaches, I would love to see, for example, a difference, but of at least 2 goals in the final score, or at least 3 goals in the final score, of difference. So it's statistically significant, the difference, but it's not simply they are different. No, they are different by a certain number. Ooh, then it's much better. Yeah. Wonderful. How clear is that? Marcelo, on the other class about one sample t, you gave us an example to calculate the t-value on Excel. Yes, I can show you guys, for sure. I ask about sample size for inspection because I'm starting a project that I will implement. PPM, DPMO indicators and the process. Oh, that's great, Henrique. That's amazing. That's amazing. I produce 5,800 parts per week. How to define the sample? Yeah, it's not simply like take 100. No, it is not. Yeah, if you are collecting PPM and DPMO, if this is discrete data, you have one approach. If it is continuous data, it's another approach. Yeah, it's there is a topic, Enrique, and we can plan like a session specifically about that, but deep dive on the, let me show you here. It's under quality tools. That's where you need to go. Stat, quality tools, acceptance sampling by attributes, by discrete data, acceptance sampling by variables. So again, deep dive on this, Enrique. Stat, quality tools, acceptance sampling by attributes, acceptance sampling by variables. Okay, it will be very helpful for you. We do have some like classic sample size that we can use as initial references, like the famous 30, 100 for capability analysis, 40 for regression analysis, 60 for gauge INR, 3 operators, 10 parts, 2 replicates. What else? 300 for attribute agreement analysis, but for inspection, for hypothesis test, we don't have like, for true sample T, you must use, 10 data points, 20 data points. We don't have something like that. Yeah, it doesn't exist, in fact. Yeah. Just before I show you guys here how to calculate T, please let me know if we are clear so far on this main conversation about hypothesis test. Let's try to summarize. Hypothesis test is under the umbrella of inferential statistics. We are looking at samples and trying to infer, to project about the population. We will be dealing with confidence intervals, so it's a probabilistic approach. It's not deterministic. It's not like a point estimate. It's not only calculating, one simple data point. Let's just calculate the mean of this sample. No. We have a probabilistic approach with these intervals, confidence intervals. Yeah, are you guys following me? And then our final decision will come from the p-value. If p-value is low, then we reject the null hypothesis. But we need to pay attention also on this battle between practical significance and statistical significance, okay? And then one of the ways to manage that is to check the difference. You are arguing about which difference. Yeah, is this practical? Yeah, from 0 to 10, how happy are we? Then one of the most famous hypothesis tests is one sample t, basic statistics, one sample t. And here we are just having fun, okay, guys? So 10. Yeah, let's see if this is a good example for you guys. Yeah, I think this is a good example. So if you guys want to understand like how we calculate these statistics, here we have sample size, just the mean, standard deviation of the sample, then standard error of the mean. Standard error of the mean, very simple. Standard error of the mean is nothing but standard deviation divided by square root of sample size, okay? Square root of sample size. So and remember that there is we'll have a rounding error here because of the number of decimal places, but it's 0.0833 divided by square root of 10 divided by square root of 10. Okay. Let me see if I not power 2, square root, power 0.5. Yeah, so again, there is a rounding error here because of the number of decimal places. If you increase here for 16 and here for 16, you may want to take like the, oops, copy and then paste here. Yahoo! 0.088 250. Yeah, with 6 decimal places will be good. So 0.02791. Yeah, and then the t-value is super simple. Okay, t-value is super simple. T-value equals, see that we have the sample mean and we have a hypothesized mean, okay? Hypothesized mean. So let me put a few decimal places here. 2, so 9.43. So it's a sample mean minus hypothesized mean divided by standard error, okay? Divided by standard error without the equal, okay? And so sample mean is 9.4368, 9.4368 minus 10 divided by this guy here, yeah, minus 20.18. This is the t-value. And then in order to get the p-value, the problem is that here 0, it's not that cool. Let's try to have another p-value that is greater, so we can see the 9.4. Yeah, this one will be very cool. This one will be very cool. So again, the t-value is nothing but a 94368 minus 9.4 now. 9.4, but then the standard error is different. It's no, it's the same. I'm sorry. Yeah, so 1.32. Beautiful, with 2 decimal places. Now, if you want, based on the t value, if you want to understand p, it's very cool. This is an absolute nerd conversation, okay, guys? This is fully nerd. Type fully nerd. Nerd. Probability distribution, okay? Then you wanna view probability, yeah, p-value, you wanna view probability. Now you wanna check for the t distribution, okay, t distribution. How many degrees of freedom? Who remembers? Degrees of freedom, we have sample size minus 1, so we have 9 degrees of freedom. And the x value is the t. So 1.32. That's the t value, you know. It's x because it's general, you know, t value. So if this is right, let me see if this is correct. No, it's two-sided. It's two-sided. Two-sided. 1.32. It's two-sided. Let me see if this is correct. We got boom, boom. Yes, correct. Yeah. So if you add up, calculator 0.1097. So calculator 0.1097 0.1097 times 2. Now you may cry. Now you may cry. And this is because it's two-sided. Yeah. If you run a one-sided test, yeah, this one is even easier to visualize. If you want just one-sided, then we would have this one here, 0.1097. 0.1097. But if you have two-sided, then you have to add up both. Marcelo, how much does this conversation impact my career as a black belt? Minimal. What's the chance of getting some mental health problems if you deep dive on that? It's very high. Very high. No. I'm joking. Guys, yeah, this is more of an academic conversation. Yeah, this is not a very practical conversation. This is more interesting than relevant, to be honest, okay? Again, this is more interesting than relevant, okay? Just if you like math, if you like, on a practical point of view for black belts and master black belts, you need to know that we are inferring, we need to collect the sample in the right way. Let's run, let's use a statistical strategy, let's look at the p-value, and let's make assertive decisions. Based on that, let's buy a new machine, let's change the layout, let's change the supplier. Wonderful. Guys, I know we went a little bit off, maybe I got too excited. Normally I keep this within 1 hour, but I hope you guys enjoyed. This is a very relevant topic, very relevant topic, applicable for root cause analysis, but also for the final project validation. Hypothesis test is a very relevant topic, okay? I hope you guys had fun. Thank you so very much. This session will be available for you, okay? So if you want to rewatch, if you want to share, feel free, okay? Bye-bye, guys. Thank you so very much. And for all my black belt students, I'll see you guys soon. I'm looking forward to celebrating your black belt certification. Bye-bye. Thank you.